Good morning friends. In chapter 14 semiconductor electronics we discuss about the numerical of exercise, right? 14.2, 14.8 and 14.9 we already discussed. In 14.2 we find out the number density of the electron and also the hole, right? And 14.8 and 14.9 we do the waveform of N and OR gate 4 given two inputs A and B. Now the same numerical we are going to discuss one more from illustration 14.10 and two from exercise 14.7 and from additional exercise 14.8. First we discuss about the 14.7 of exercise. Right. What is given? A PN photodiode is fabricated from a semiconductor with the band gap 2.8 electron volt. Can it detect a wavelength of 6000 nanometer? So already we discussed in theory portion the photodetector or the photodiode is used to detect the wavelength of incident light. If the energy corresponding to the wavelength is greater than the band gap energy of the semiconductor from which the photodiode is prepared, at that time this wavelength can be detected by the given photodiode. If the energy corresponding to the given wavelength is less than the band gap energy, so this wavelength cannot be detected. For that purpose here, the band gap energy EZ is given 2.8 electron volt and wavelength lambda is equal to 6000 nanometer are given. Therefore, the energy corresponding to the wavelength lambda corresponding to the given wavelength is E is equal to, we know the equation of the energy E is equal to hc upon lambda, hc upon lambda, that is in joule. To convert into the electron volt, that is in joule. Therefore hc upon E lambda, that is in electron volt. We substitute the value as Planck's constant 6.625 into 10 raised to minus 34. See, velocity of light in vacuum 3 into 10 raised to 8. 3 into 10 raised to 8 upon wavelength 6000 nanometer, therefore 10 raised to minus 9. 6000 into 10 raised to minus 9 and E 1.6 into 10 raised to minus 19 charge of an electron. As we simplify it, we obtain the value of E is 0.207 electron volt. That is the value of energy corresponding to the given wavelength. Thus, given wavelength cannot be detected. Here, E less than EZ. So, given wavelength cannot be detected or can't be detected by photodiode. Again, here a PN junction photodiode is fabricated from a semiconductor with a band gap 2.8 electron volt. Therefore, band gap energy is 2.8 electron volt is given. Can it detect a wavelength of the 6000 nanometer? So wavelength is given 6000 nanometer. That means the 6000 into 10 is to minus 9 meter. The energy corresponding to the given wavelength E is equal to hc upon lambda, that is in joule. So it's equal to hc upon E lambda, that is in electron volt. So we have to find out the energy corresponding to the given wavelength. If this energy is greater than the band gap energy, so at that time this wavelength can be detected by the photodiode. If the energy corresponding to the given wavelength is less than band gap energy, so this wavelength cannot be detected by the photodiode. Therefore, energy we obtain, there is the 0.207 electron volt. But band gap energy is given the 2.8 electron volt, so E is much less than the EZ. So given wavelength cannot be detected by a photodiode. Clear this? Okay. After that, from additional exercise 14.8, the same type of the numerical we discussed in illustration 14.2. The number of the silicon atoms per meter cube is 5 into 10 is to 28. This dopant simultaneously with 5 to 10 is to 22 atoms per meter cube of arsenic. 5 to 10 is to 22, that is the atoms per meter cube of arsenic are added in this silicon atom. Right? Here the arsenic is which type of the impurity atom? There is the donor impurity atom because there is the pentavalent. And also 5 to 10 is to 20 per meter cube of indium. That means in one type of the semiconductor is given silicon, at one end arsenic atoms are added, other end indium are added. Here the proportion are given. Therefore, the numbers of the arsenic atom, numbers of arsenic atoms per meter cube is, arsenic is the donor impurity atom. Therefore, Nd is equal to 5 into 10 is to 22 per meter cube. And indium are added 5 to 10 is to 20 per meter cube. Numbers of indium atoms per meter cube is Na. Indium is the acceptor impurity atom because there is the trivalent. So only the 3 covalent bonds are formed, 4th is not formed. Therefore, it has the acceptance of the electron. Therefore, these impurity atoms are known as the acceptor impurity atom. That is given 5 into 10 is to 20. That means the 0.05 into 10 is to 22 per meter cube. Now, the numbers of the electron, we have to find out the number of the holes and electrons. The Ni, intrinsic charge carrier density, is given 1.5 to 10 is to 16 per meter cube. And after adding the arsenic and indium, so this material is P-type semiconductor or the N-type semiconductor, we have to discuss this thing. For that purpose here, the numbers of electron Ne is equal to Nd minus N. Nd minus N. Nd is 5 into 10 is to 22 minus Na 0.05 into 10 is to 22. 10 is to 22 common, therefore 4.95 into 10 is to 22 per meter cube. That is the number of electrons. Now we have to find out the number of holes. We know the equation, but Ni square is equal to Ne into Nh. Therefore, Nh is equal to Ni square upon Ne. Ni, that is given 1.5 into 10 is to 16 whole square upon number of electron 4.95 into 10 is to 22. So as we simplify, we obtain the numbers of the holes 4.5 into 10 is to 9 per meter cube. That is the number of holes. And that is the number of electron, number density. So here, which type of the material is formed? N type or the P type after adding the arsenic and indium impurity atoms. So here the number density of the electron is much more than the number of hole. So there is the 4.95 to 10 is to 22, here only 10 is to 9. Here Ne is greater than the NH. So material is N type because the number density of the electron are more, therefore the majority charge carriers are electron. Therefore this material is N type. Now listen, here the two types of the impurity atoms are added in silicon crystal. So arsenic and indium, arsenic is the donor impurity atom. Therefore numbers of the atoms per meter cube of arsenic, that is the Nd. And due to the adding of the indium, the number of accepted impurity atoms are 5 to 10 is to 20. We add down in the same form of Nd. Therefore 0.05 to 10 is to 22. Okay. Numbers of the electron, that gives the difference between the Nd minus Na. So that gives the numbers of, or the number density of the electron. Therefore N is 4.95 to 10 is to 22 per meter cube. But we know that Ni square is equal to Ne into Nh. We can find out the Nth number of hole, Ni square upon Ne. So that is the 4.5 to 10 is to 9 only. Right. Here, number density of the electron is much more than the number density of the hole. Therefore, the majority charge carrier in whatever the material is prepared is electron. Therefore, this type of the material is N type. Clear this? Okay. After this, now we are going to discuss about the illustration number 14.10. Already the same numerical we discussed in 14.8 and 14.9 illustration. We do the waveform of OR and AND gate for given two inputs A and B. Here the two inputs are given in terms of the 1 and 0. We have to prepare the truth table and also we have to sketch the waveform of only output of NAND gate. But here we prepare for all the gate. Right? That is very easy for us. Now A and B. Here the inputs for different time interval are given T less than T1, A1, B1. T1 to T2 both are 0. T2 to T3 A is 0, B is 1. T3 to T4 A is 1, B is 0. T4 to T5 A is 1, B is 1. T5 to T6 both are 0. And T greater than T6. That means after the time T6, the A is 1, B also 1. First we enter the truth table for OR gate. For OR gate. After AND gate, then NOR and for null. Now Boolean equation of OR gate. Boolean equation for OR gate. There is the A plus B. Y is equal to A plus B. So for OR gate, the Boolean equation is A plus B. Y is equal to A plus. What is the characteristic of OR gate? 0, 0, 0. For OR gate, the characteristic is 0, 0, 0. That means the output is 0 if all inputs are 0, otherwise 1. Again, in OR gate, output we obtain 0 only if both inputs are 0. So in Z, that is the both inputs 0, 0. So here the output is 0. Here 0, 0. Otherwise 1. So that is the truth table of OR gate. Again, the characteristic of OR gate is 0, 0, 1. So as the A, B, both inputs are 0, output is 0. Otherwise 1. So 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, again 0, 0, 0, 1, 1, 1. Now next for the AND gate. AND gate, the Boolean expression is y is equal to A dot B. We know for the AND gate, the output is 1 if both inputs are 1, otherwise 0. For AND gate 1, 1, 1, OR gate 0, 0, 0. Right? Okay. So how we prepare the truth table? If the both inputs are 1, at that time the output is 1, otherwise 0. A and B1, therefore 1. A B1, 1, otherwise 0. So that is the 0. That is the truth table of AND gate. Keep in mind this characteristic for AND gate 1, 1, 1. If all inputs are 1, output is 1. So here A and B here, that is the 1, so output 1. Now next, here 1, 1, 1. Otherwise 0. Okay. Here we first do the waveform of OR AND and AB. Now listen, for A input, there is the input A. There is the time T1, there is T2, T3, T4, T5, T6. Less than T1, A is 1. Less than T1, A is 1. This. T1 to T2, 0. So waveform of A is this. T2 to T3, again 0. T3 to T4, 1, and T4 to T5, 1. T3 to T5, 1. There is the waveform of A. Now T5 to T6, 0. T6 and more, that is the 1. So there is the waveform of input A. Now what is the waveform of B? 1, 0, that means below the time T1, there is the 0. There is 1, sorry. There is the B. T1 to T2, 0. T2 to T3, 1. T3 to T4, 0. T4 to T5, 1. T5 to T6, 0. And T6 and more, there is 1. So there is the waveform of B. Right? Okay. Now from this to input, what is for the waveform of OR gate? For OR gate, if the both inputs are 0, at that time the output is 0, otherwise 1. Otherwise 1. Now listen, here there is the 1, 0, 0, 1, 1, 0, 1. For B, there is 1, there is 0, 1, 0, 1, 0, 1. For OR gate, if both inputs are 0, output is 0. Otherwise 1. Only for these two time intervals, the output is 0, otherwise 1. So that is the waveform of OR gate. Waveform of OR gate. Now for the AND gate, again we check for the OR gate. First is the 1, next is 0, next 3, 1, 1, 1, 1. Next is 0, 1, 0, 1. So both are same as our table. Now for AND gate, AND gate has the characteristic is 1, 1, 1. If the both inputs are 1, output is 1. 0, again 0, 0, here the 1. 0 and last 1. So only for this 3-time interval the output is 1, otherwise 0. So now 1, both inputs are 1, therefore 1. Now 3, 0, 1, 1, 0, 0, 0. Again 1, 0. And now both are 1, so here we make the row that is also 1. So that is 1. Because input has the characteristic of both inputs are 1, we get the output is 1. Now for NOR gate, what is the characteristic of NOR gate? NOR gate has the characteristic is that if the both inputs are 0, output is 1. Output is 1. If both inputs are 0, output is 1. So here both inputs are 0, output is 1. Otherwise 0. Otherwise 0. So there is the inverted output of OR gate in NOR. NOR has the output is inverted of output of OR gate. OR gate has the output is 0 if both inputs are 0. NOR gate has the output is 1 if both inputs are 0. Therefore, for these two, both inputs are 0, output is 1. Again, here in this case, the both inputs are 0, output is 1. Now here we do the waveform 1, 1, 1. Here 0, 0, that is the 1. 0, 0, that is the 1. Here again 0, 0, that is the 1. Otherwise 0. So that is the waveform of the NOR gate. Waveform of NOR gate. There is the inverted image of OR gate. As you pull down the waveform of OR gate, so that be this OR gate. Now, so that is the 1. Sorry, that is the 0. That is the 1. 0, 0, 0, 0, 1, 0, 0, 1 and 0. Now, what about the NAND gate? Now, the Boolean equation of the NOR gate is y is equal to a plus b bar. Y is equal to a plus b bar. Not all. That means the 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. The same way, 1, here 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. Now for the NAND gate. NAND gate has the characteristic is that if both inputs are 1, output is 0. Output is 0 for NAND gate and 1 for NOR gate. Again, if the both inputs are 1, output is 0 for the NAND gate. So keep in mind this characteristic for NAND gate. Boolean equation is y is equal to a dot b bar. Y is equal to a dot b bar. So this is the inverted of AND gate. Inverted of AND gate. Now we keep in mind this characteristic if both inputs are 1, then 0. 1, 0. Last also 1, there is 0. Otherwise 1. Now there is the inverted of AND or not. 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1 0. Now keep in mind this characteristic 1 1 at that time 0. 1 1 at that time 0. Again 1 1, that is the 0. 1 1 again the 0. Otherwise 1. So that is the waveform of NAND gate. That is the inverter of this. Inverter of this. Now AND gate 1, so inverted 0. 0, 1. 0, 1. 0, 1. 1, 0. 0, 1. 1, 0. So only we have to obtain this waveform in this question, but we do for all the gate or and low and also the NAND gate. And also we prepare the truth table for all this gate with the Boolean equation. For different time of interval, the inputs A and B are given. Right? So very easy, we can prepare for this practice. So our concept about the characteristic of OR gate, AND gate, no and none is going to clear. So for any given inputs, for any logic gate, we can do the output. Clear it? Okay.